Well, finally, we come to the key equations. There's only two of them. Only two of them. The first one, we call it a state transition relationship. Your current position equals your previous position, multiply something. If you look at the tracker example, this Fk is nothing but an identical matrix. Or maybe not, you include the velocity or some other matrix. And this could be the acceleration and the orientation change, direction change. And the Wk is the noise. We call it white noise, means this is a random error. We simply understand everything has an error, and we don't know this either. So, but the relationship is there. The underlying relationship is this. Your current state equals your previous state times the transition matrix plus a control variable times this control transformation matrix and times the error. That's the first equation. The second one is about the measurement. And your measurement does not quite equal the prediction. So if I measure myself is in 3-4, I might not be in the 3-4 position. My GPS could be right, give me 5-6. And then you get another error. This is also, again, a random matrix. Depends on the calculation itself. But the measurement always equal HK, another transformation to your position. Of course, what you're measuring is maybe not exactly the position. For example, GPS, you measure the distance to satellites, but your XK is your position. And you can calculate or approximate this difference by the distance formula. You know your prediction, you know the satellites, then you can also use this information to compute where you predict yourself is, and then what distance you predict yourself have to the 5 satellites. And that prediction is right here, and the real measurement is right here. They're not the same. How much difference? Again, by a normal distribution of the random error. Okay, that's the relationship. What I said? Back to the track example, you might understand a little better. So if back in the track example, the XK is going to be position, velocity, and the transition matrix, we know the XK equal XK plus minus 1 plus Vx times the dt, the time. The time usually is 1, dt equal 1 unit. The Yk equal Yk minus 1, that's last position, plus Vy dt. And then what else? Vxk equal Vxk minus 1, depends on the acceleration. That's a kind of transition matrix. And the B, we can talk a little later. The bottom line is they always have this normal distribution noises. Now, we got a little more and more detail each time. And the more move from the qualitative process to the quantitative computation. So in the real computation now, I'm not talking about qualitative model. To the real computation, what you need? you need the input f. That's the relationship you know before any calculation. B, H, and the QR are the noises, at the random error. That's what you need to know to write your code. And you also need to have a start point. You can, and the start control variable, like the truck example, you can think about your original position, just 0, 0, 0, that's fine. And you can think about your noise is just like 25 times 1, 1, 1, 1, the rest all 0. That's fine. You need to give this to start the computation. Then you start it. Once you start it, you enter into the two phases cycle. And in each cycle, what you need to know? You need to know the estimate of your previous estimate, previous stage. Now look back into here. For the next stage, you do the calculation, and this, it really, look at this error, really come from what? From your calculation here. Because in one stage in here, you get your posteriori calculation like this, and now goes to 4, and this, you know it, and this, you know it. The next stage, it will be 4, 3, 4, 3 here, and this will be 4, 4, and the 4, 4 here. And then after 4, then your k equal 5 will replace k equal 5, then you know the 4, 4 here, and then this is 5, 4, a little bit messy, but you got the idea. And then this is 5, 5, so on and so forth. That's the calculation. Well, the bottom line you observed in both key equation here, you got this noise. What is your goal? Your goal is to minimize those. You make this white noise as small as it can. So all this calculation is related from your error of the posteriori state estimate. For that, your goal is to minimize the trace of this. And how do you get the k-mark gain? That key constant, k-mark gain, really is the parameter. If you are put such a gain, that will going to minimize this posteriori covariance, or in another word, minimize your error. That's all about the error model. So again, it's the whole idea of the least square error model. So how do you get those k-mark gain? Take the partial derivative. You don't know the k-mark gain in the beginning, but you do know you want to minimize that. And then the Lagrange's method, just take the derivative, find the critical point. Then you're going to solve the k-mark gain. And once you solve the k-mark gain, then you update your estimate. And after you update your estimate, you're going to make sure this new one, as the covariance, will be smaller. Your error reduced because you found the right blending factor. And we're going to explain a little more. Let me think.